Hello, my curious friends. This lecture is about fluids in motion. Fluids in motion can be quite complicated, but we will mainly focus on what we call laminar flow. Here in this picture, you see smoke coming out like nice straight lines. That's what we call laminar flow, and then it just mixes and turns and so on, what we call turbulent flow. So we'll be omitting turbulent flow, which is very complicated, focus on nice smooth straight line flows, which is called laminar flow. Simply, that's what we're going to focus on. We will also assume that the fluid is incompressible, which is a pretty good approximation, and inviscid. Viscosity is actually important, but at the limit we are learning it, we will ignore viscosity. Fluid flow, and when we're concerned with water, ignoring viscosity is pretty well approximation. In healthy areas, blood flow, if it's larger arteries and veins, it's pretty good approximation as well. But if we go to smaller capillaries, then viscosity becomes important. Viscosity is simply fluid's resistance to flow. So like resistance in similar to friction or air friction, we can say something is trying to move and there's something preventing it, some force, which is viscosity in terms of fluid flow. In more complicated works, people look at what is called Reynolds number, which is relating the fluid flow. Here we have density times velocity times length. The fluid is flowing, divide by the viscosity to see if viscosity is important or not. This is again called Reynolds number. If we have high Reynolds numbers, that means viscosity is small and ignorable. This is for water here that flows at 1 meters per second. If we have low Reynolds numbers, that means viscosity is important. This is for if blood moving in an arteriole, we have a smaller Reynolds numbers. But overall, with this, for the simplicity, we will ignore Reynolds numbers or viscosity. We will assume we have flow that is laminar, very straight lines and easy to deal with, inviscid. Incompressible means we can't compress it. It doesn't. Its shape can change, but overall volume cannot be changed. One important aspect we're going to focus on is called continuity equation, or equation of continuity. That comes from the fact that fluid is incompressible, which is a very good approximation to a very good limit of the fluids we'll be dealing with. Water, even for air, it's a good approximation, and blood as well. And continuity equation deals with idea that if we have an incompressible fluid, there's a block of it, a volume of it going into in one region of flow, and a volume going out should be equal to each other. So what we call volume 1 delta V1, this is capital V here, is equal to volume 2 delta V2 here. And if I just calculate that volume, it's this area here for 1, right, times this width of it. So A1 delta X1, and the same here. They should be equal to each other. Using a simple knowledge we have from motion, we know delta X is equal to V delta T, and time of going in for a parcel of fluid to going out should be the same. So we can replace all delta X1, delta X2 with V1 delta T and V2 delta T. And we'll end up getting this equation here. And this equation, canceling delta T's, will give us what we will be working on. A1 delta T, A1 V1 is equal to A2 V2. So area 1 times velocity 1 is equal to area 2 times velocity 2, which is called continuity equation, or equation of continuity, meaning that the parcel of fluid, volume of fluid going in to a flow region should be equal to the volume of fluid going out of the flow region. It's equal here and equal here and equal everywhere. if you look at it in the same amount of time, delta t. This gives us this idea. If I have a larger area, I will have a smaller speed to keep the continuity equation continue. And if I have a smaller area, I'm going to have a larger speed as a fluid. A times V, area times the velocity through that area, is also called flow rate, Q. It comes from the volume over delta T. We can derive to show that that's equal to velocity times the area, which is actually what we did here. So you can also say then flow rate 1 should be equal to flow rate 2. The same idea here. This will be one important thing we'll be focusing on. And it's again tells us that if we have a flow going through a large area, and if we decrease that area, flow speed increases. And we always do this when we're watering our garden and so on. We decrease the area, and the water is coming at the same volume, so it has to get out. To get out, it has to increase its speed. And incompressibility requires that. You might also notice, might have already noticed that if we let the water flow, this is kind of a free fall, right? And water here is slower than there. And as it gets faster and faster, we see, so if I draw here a V1 is smaller than V2, not VI, V1. And draw here V2 will be larger due to free fall. We know free fall, right? And as the velocity gets larger, area gets smaller to keep continuity equation or rule of continuity. So if I take a parcel of water here and watch it over a time, take another one, watch it over the same amount of time, these two parcels should be equal to each other. And that maintains the fact that the velocity should be larger for a lower volume, smaller areas. A simple question might be involving just the idea that large area, small velocity, small area, large velocity. Like a quick check here, we are seeing water flows from left to right through this pipe. What can we say about the speed of the water at points 2 and 1, 1 and 2, V1 and V2? If I look at this area here, it's definitely larger than this area here, A2. And writing down my continuity equation, A1 V1 should be equal to A2 V2, tells me that if I have a smaller area here, I should have larger speed, so this equation can hold. So this tells me V2 is larger than V1. And here is the explanation. Here is the answer given here, the same idea there. As I mentioned in the beginning, we will be focusing on laminar flow, nice flow lines, and we can imagine flow lines along the flow. They will be going smoothly. Velocity at any point on the flow lines or streamlines will be tangential to the streamlines. Over here is shown as V. I can show other ones. So if I have flow lines shown for me or streamlines shown for me, I can find the direction of velocity using that. Streamlines never cross each other, and if I look over a streamline and watch a parcel of fluid going, its shape could change, but its volume will stay constant. Continuity equation maintains that. And still A1 V1 equals to A2 V2. So if I call this V1 and call this V2, I can safely say that V1 is larger than V2. I have a larger area here, smaller area there. Again, continuity equation, A1 V1 equals A2 V2. All right, and here's the second idea we will focus on, called Bernoulli's effect. Bernoulli's effect simply says that since we have in larger areas smaller speed, smaller area larger speed, there must be a pressure, a force pushing the fluid through this narrower area to cause that. And the pressure where we have a larger speed will be less than the pressure where we have smaller speed. because again, that should be a pressure pushing the fluid into this narrower area, very simply. So that boils down the facts listed over here. To accelerate the fluid, the pressure must be higher in the wider part, which I have said. That means there's a pressure difference from here to here. This is called pressure gradient. If there's a pressure difference, we call it pressure gradient. I have a high pressure here, low pressure there. There's a difference. Gradient means there's a pressure difference. So there must be a pressure gradient from larger area to smaller area. This also tells us that an ideal fluid again will have a laminar flow, nice smooth flow, no turbulence, and it will be inviscid, no viscosity, and incompressible. So an ideal fluid accelerates whenever there is a pressure gradient, which makes sense because if we have a larger pressure here, smaller pressure there, this part will be pushing on. The left part will be pushing on the right part, right? And these arrows show that. There is an acceleration from here to there, so increase in speed. The pressure is higher at the point along a streamline where the fluid is moving slower, lower where the fluid is moving faster, which makes perfect sense. If there's a pressure pushing here, acceleration from left to right, that means here I have smaller speed, here I have larger speed. So all the same thing goes around and comes back. The idea that if there's a pressure gradient, there will be a push from larger pressure to lower pressure, and that happens when we are going from larger of cross-section areas to lower cross-section areas. Goes back to the same idea we talked about before. Continuity equation, A1 V1 equals A2 V2. Same parcel of fluid should pass through here, so it should increase its speed. If it does increase its speed, there is a larger pressure here. Let me show that too. And lower pressure there. Once we decide that things are pushed in this direction, this pressure is pushed on that way. So we have larger speed here. Larger area, this would be my A1, and smaller area. Okay, the bottom line is, if I have a flowing fluid that goes from a larger cross-section area, if you look at this bottom figure here, summarizes it, to a smaller cross-section area, it speeds up. That's due to continuity equation. So V1 is smaller than V2 here. And when it speeds up, that means there's a larger pressure here pushing things to the right. So if I look at pressure here, the fluid pressure here, P1 and P2, P1 will be larger than P2. So velocity and pressure, fluid pressure, is inversely proportional to each other. These lines are showing how much fluid is pushed up, right? I have outside atmospheric pressure here pushing down. Let me do a better job there. So I have P0 here everywhere, right? Pushing down the fluid. And fluid flow pushes it back up from down, right? So everywhere we have this P0. And the larger this push, this pressure, fluid pressure pushes in all directions equally. So P1 also pushes up here, up there, everywhere. Okay, P1. So P1 pushes some fluid up, and we have some rising of the fluid against P0 on the left. And the same happens here. P2 pushes up too. Okay, let me do a better job there. All right. P2 pushes up, P0 pushes down, but P2 is lower than P1, obviously. So it pushes the fluid up less than P1. So by looking at this, just how this fluid looks, larger area to smaller area, velocity increases, pressure decreases, or how much fluid is pushed against the atmospheric pressure can tell me which pressure is larger. P1 is larger than P2. So the fact that velocity larger, pressure smaller, velocity pressure are inversely proportional to each other is called Bernoulli's effect or Bernoulli's principle. This is a questions as examining what I've just showed you. We have liquid here and another liquid flowing here up here. We don't know the shape of the container it's flowing in. Let's call them VA, VB, VC. And it goes out in here. Well, gas flows, but we take it as fluids. Gases can be also considered to be a fluid, like air will consider to be a fluid. Flowing gas here also behaves like fluid here. It's flow, it has a velocity. And we have two information now. A1 V1 equals A2 V2. So that tells me this is continuity equation. That tells me if I have a larger area, I have smaller speed. If I have a smaller area, I have larger speed. So area and speed are inversely proportional, or velocity, area and velocity. Remember, if I say velocity, I mean speed with direction, are inversely proportional. Okay, that's what this tells me. That's continuity equation, continuity rule. And additionally, we learned pressures and velocity are also inversely proportional. We don't have an equation for that yet, but we will get to it. So that's what we know so far, and this is called Bernoulli's principle. I'm not sure if it had an E here, but I'll check that. Bernoulli doesn't have an E. All right, no E. Bernoulli's principle. Okay, high pressure, low velocity. Low pressure, high velocity. So gas flows from left to right through this pipe. We have a pipe, we don't know its shape, whose interior is hidden. We have a pipe in here, we don't see. At which point does the pipe have smaller inner diameter? So I'm looking about the cross-section areas, right? If I have a pipe, let me draw it in here. In round shape, cross-section area can be calculated using its diameter, right? If this is diameter, we look at the radius, right, r, and the cross-section area will be pi r squared. So large r, large cross-section area, or large diameter, large cross-section area. Which one has the smallest inner diameter? Let me do my thinking. Diameter and velocity are inversely proportional. So if I'm looking for smallest diameter, right? Since velocity and diameter or area, cross-section area, inversely proportional, smaller diameter means smaller area, right? So smallest diameter will be corresponding to largest speed. So I'm looking for where is the speed largest, okay? And to find, let me spell this better. To find where the speed is largest, I'm going to see how much fluid is pushed down. Here, gas pressure is pushing down. Here I have gas, maybe yellow is not a good idea. Let's use green. I have gas pressure pushing here, right? At point A, at point B, and at point C. These are all different pressures depending on how fast the gas is flowing. And if I look here, column PA, PB, and PC, so I'll call this pressure A, call this pressure B, and pressure C. It's obvious that pressure C is the largest. It pushes the fluid most. And then I have a pressure A and then B. So I have this. Pressure at C is larger than pressure at B, and it's larger than pressure at, oh no, not, I put it wrong, sorry. Pressure at C is larger than A. I said it right and write it wrong. Alright, sorry folks. PC is larger than PA is larger than PB. So the largest is C. And Bernoulli's principle tells me the larger the pressure, the smaller the velocity, inversely proportional. So if I want to compare velocity, C has the smallest velocity, and then A, and then B. Now as far as the areas go, area and velocity through continuity equation are also inversely proportional. So if I want to compare the areas, which is directly proportional to diameter from this discussion over here, areas goes inverse. So I have area at C should be larger because velocity is smaller than area at B at A, and then area at B. So the smallest area is B. I'm looking for smallest diameter. That will be where we have the smallest area. Here is the answer, and this figure is nicely showing how we have larger area, we'll have smaller speed as a sample here from continuity equation. This dude over here, we will say that large area, small speed, small area, large speed. And we also know from Bernoulli's principle that we don't have any equation, but we know if we have smaller speed, we have larger pressure, and vice versa. That helped us decide where we have the smallest diameter or smallest area, which is B. Other facts we will have in this section involves conceptual questions relating to, for example, in atmospheric flow, wind, right? We have wind flow, and quite often it's also laminar nice flow. And as it goes, for example, over a hill, we can draw streamlines, and as the streamlines get closer, we have faster speed. So that's one fact we can start from. We have, if I say here V1 and V2, V2 is larger than V1, I can decide, because streamlines are getting closer. And if that's the case, Bernoulli's principle tells me P2 is smaller than P1, inversely proportional to velocity. Okay, so this is all related to Bernoulli's principle. And again, human beings are smart. So what we did, we took that idea and applied it to flying. We built a wing for our airplane. So as the air goes through and up here, up in the wing, the streamlines will get closer. So we will have faster speed here. I'm going to call this, what's happening here? Let me try that again. So I'm going to draw a speed here and a speed there. Okay. If I call this V1, and V2, streamlines get together, so V1 is larger than V2. If that's the case, P1 is smaller than P2. Now pressure is force divided by the area, right? So there's a pressure up here, P2, pushing up, and P1 pushing down, or force pushing up and down, F1, F2, okay? And P2 is larger than P1 because of speeds inversely proportional to pressures, and that causes an overall net force that is upward. F lift would be force due to P2 minus force due to P1. That's difference. There you go, your connection with pressure to Newton's laws. F is equal to ma. If I want, I can now calculate what is the acceleration of upward, right? So if I know this pressure, that area, I can divide it, I can find force using pressure is equal to force divided by the area. That means force is equal to pressure times the area. So I can calculate even that net force, calculate acceleration. That would be a very nice integrated question. Maybe we'll do one. Bernoulli's effect is applicable to real life in many different ways. For example, when we use a perfume, we get out perfume by pushing on a pump, and that accelerates air around the part where we are getting the perfume out. So pressure drops and the gas pushes out. If there's a wind blowing over our hand during a storm, for example, it gets faster. That's why mostly the earliest part to go for a storm is the ceiling of our home, because we have V fast here. V gets faster. That means pressure drops. So the ceiling goes off. If you're driving really fast in a highway and you're close to a track, try to don't really speed up too much, don't get too close, because the air in between you and the track gets faster. If it gets faster, pressure drops here. So you're pushed towards each other. Possible collision. Avoid that. Know your physics. Bernoulli's principle can be studied further to come up with an equation that can relate pressures, velocities, and heights in a system. So if let's say we have our sewer system, we have our water system, water drainage, and so on. These are all taken into account as the people build those. And the simple idea is work done is equal to change in energy. So if we calculate work done, force times the distance, and equate it to energy change in kinetic and potential, we can come up with this equation. Simply we push a parcel of fluid here, do some work done here, that pushes a parcel of fluid over here. So we can find the total work done using work here minus work there. And then we have kinetic energy here, kinetic energy there, potential depending on how high the fluid is, rho gh, and work out the equation, which I'm not going to do here. We can come up with an equation relating the pressures. Pressure is actually related to dense energy. So simply energy per unit volume can be defined as pressure. So we come up with this equation, which is called Bernoulli's equation. If I have points 2 and points 1, fluid pressure at points 2, P2, plus, this can be called kinetic energy density or dynamic pressure, 1 over 2 rho V squared, at this point 2, V2 squared, plus rho g y2 would be this height over here. At this point is equal to corresponding values in the point 1, P1 plus 1 over 2 rho V1 squared plus rho g y1. Okay. We generally take the height as the center of the fluid pipe. So here y1 will be 0, y2 will have this height. I'm going to replace these by rho gh. I want to study this with you via a question, which will be a type of questions we'll be practicing. We will have one in class, probably one in the review session next week. All right, so here's a system. We're looking at the part of a system, right? And water flows from left, goes up a little bit, and goes out in there. All right. The water speed through the lower pipe is given here. I'm going to call this V1. So I'm going to call the left part 1, right part 2. Oh, they already did that. Okay, awesome. And the pressure at this point is read as 75 kilopascal. Kilo is always 1,000, so that's equal to 75,000 pascal. I'm just going to put it here. Okay, one more zero. All right. The diameter of the lower pipe is 6 centimeters. This is the D1. 6 centimeter. I'm going to convert it to meter right away. Actually, I'm going to write down the R1. D is the diameter, the whole distance here, right? And R is the radius. So I'm going to look at R because I need R1, for calculating my area A1 if needed, right? That will be my A1. So R1 is equal to 3 centimeters. Divide by 100, 0.03 meters. I'm hoping you guys are all on board with this, and it's a simple fact for you. All right. And that of upper pipe, so V2, I don't know, not given. And it's actually part A of questions asking me that. And I know the radius for this area too as well. So I'm interested in this area too to find V2, which is why I'm putting that in here. And R2 is equal to 2 centimeters because diameter is 4, R is 2, half of that, and 0.02 meters. These are all the values we have. Now, A. What is the speed of the water on the upper pipe? If I'm given areas or diameters and one speed, not the other one, I am going for continuity equation. A1 V1 equals A2 V2, my friends. A1 pi R1 squared. If I have a circular area, that's how I calculate it. V1 is equal to pi R2 squared is my A2 V2. Here I'm going to divide each by pi, so these guys go away. And since I'm solving for V2, I'm going to divide each side by R2 squared to leave V2 alone, right? This guy goes. Here's what I have. V2 is equal to R1 squared V1 over R2 squared. R1 is 0.03 meters. I'll square that. V1 is 5 meters per second. Oops. And divided by R2 squared. R2 squared. 0.02 meters. Square that. I'm going to find my velocity too. All right. It should be 11.25. Assess, right? Remember, we look at the question, we write down, if there's not a picture, we draw an ugly picture, write down the notes. Then we think about what we can use to solve it. We did all that. And after you find an answer, assess. Our book is suggesting it. That means suggesting us to do. That means think about if your answer makes sense shortly. It makes sense because I have smaller area and I'm expecting a larger speed. I got a larger speed. That gives me assurance that probably I solved this right? So do a quick check, assessing as you solve the problem. Now B tells us, what is the region of pressure gauge on the upper pipe? Remember, gauge pressure was the pressure of the gas only or liquid only in this case. We know P1, but we don't know P2. I forgot to put that in, right? Now they're asking us to find that. For that, we will use, again, this is continuity equation. That's B. Not A. We did A already. B, we will use Bernoulli's equation. Okay, it's a long equation, but solution is straightforward. So all you need to do is over here add everything. You will have P1 1 over 2 rho V1 squared, rho G H1, which is 0 in this case. We're going to take the center off. the pipe. So in this case, now we have H1. We assume this is our base point, so H1 is 0. And this will be H2. And we will compare, we will equate, not compare, that to whatever we have here. So let's put that down. I'm going to show you the equation again. It could be scary in the beginning. But again, write down everything, put in knowns, solve for unknowns. It will be a plug and chug kind of, once you get used to it, question. So let's write down for the left. We have P1, pressure of the fluid, plus 1/2 rho V1 squared, plus rho G H1, very similar to conservation of energy, which is where this is actually derived from. And it's equal to P2 plus 1/2 rho V2 squared plus rho G H2. Notice here I replaced Y1, Y2 by H1, H2. That's all. Height, I like using it as H. So, and I kept the same equation from the book for those who goes the book and reads it. I'm replacing Y's by H's. Feel free to use Y. It's the same thing. Bottom line is it's the same thing. H2 or Y2, right? H1 or Y1. Since this is my baseline over here, my H1 is 0, this dude will go to 0. I cancel that. And remember, we know everything else, we're solving for this guy. Now I'm going to go my way here, my friends. If I subtract all this thing from both sides, I'm going to leave P2 alone. And here is my equation for P2 then. P2 is equal to P1 plus 1/2 rho V1 squared minus 1/2 rho V2 squared minus rho GH2. Put in all the values. Please do that. You'll find P2 is equal to 4,618.75 Pascal. Here it is given as 4.6 kilopascal. Pascal to kilopascal we divide by 1,000. It's like meters to kilometers. So that's about 4.6 kilopascal. Alright, that's all we need to know about fluid flows, flow and fluids. Two basic equations. Continuity equation, A1 V1 is equal to A2 V2. Fluid coming into a region should be equal to fluid going out of a region. Consider the same amount of time. And Bernoulli's equation is pressure continuity kind of, or conservation of energy. And we have this long looking equation which ends up being very simple to solve often. Why is this important? Most importantly in the medicine area. For example, if you are planning to go for MCAT, you do want to do some further reading about atom viscosity, how it impacts, because most importantly, flow and fluids, most importantly, is needed in health area for blood circulatory system. We have blood flows. We measure the pressure of our blood, right? Blood pressure, mainly measured in millimeter mercury, and we measure the pressure as the heart contracts and sends the blood out into our veins, which we call systolic pressure. It's a higher one. And then we measure when the heart is relaxing, which we call diastolic pressure. So if you have noticed, your blood pressure is generally given like 120/80. That's in millimeter mercury. You can convert to Pascal to see how much is that. I converted here. So 120/80 millimeter mercury is about 15,960. It was 16,000 Pascal. per 10,600 Pascal, 640 Pascal. That's a very high pressure. We have high blood pressure. It's important in keeping us actually stable under a lot of atmospheric pressure we have. Remember, 1 atmosphere is equal to 101,300 Pascal. So we bear that pressure by having our blood pressure. And of course, also blood pressure is important for sending the blood to everywhere arteries in our body. It flows with a speed, and speed changes through as it goes through the different veins and arteries and so on. Also, as it goes into from veins and arteries, the capillaries area gets larger, right? Applying A1 V1 is equal to A2 V2. As the area gets larger, we have smaller flow. So assuming this is just one pipe here and going from here to there, I'll have V1 here and then V2 here. Overall, I can estimate how much smaller, because I have larger area, right? Smaller speed, my blood will have in capillaries. And this is important for checking healthy blood flow and so on. That's why we check blood pressure. That's all, my friends. I'll see you in the next video.